And today I'm going to be discussing a little bit my research and like my trajectory, and then I want to try to talk about what quantum is and what it's not, and a little bit about transferability of quantum algorithms across different domains. So before we start talking about research, I wanted to introduce myself a little bit because, as I said, I'm pretty new to CDC. So my background is math and physics. Did a PhD in data science, worked at industry for a while, and then I did a PhD in quantum machine learning in Madrid. And after that, I spent around 3.5 years working at industry. So I worked at engineering. It's a quantum machine learning startup based in Chicago, and the goal there was to do quantum machine learning solutions for life sciences. So it was more like a consulting firm, and we developed some quantum solutions, research solutions in the areas of life and environmental sciences. And apart from that, I founded a nonprofit organization called Entangled Minds. That's a personal project that I'm pretty proud of, which is about using quantum information theory as a framework for describing certain aspects of the human mind. In particular, we're doing a project in neurodiversity. So this is a science that's very qualitative because it's psychology. And we're trying to come up with a framework that can help understand the space of neurodiversity from a more quantitative space. I'm happy to show you a demo afterwards. This is not related with anything that I'm research on, but I just thought it's kind of a cool project. And then I started at CDC this month, and I've been here since then. And one of my first tasks was actually something very interesting, which is doing like a mapping of the different CBC research lines and how these could be potentially improved or complemented with quantum computing and quantum machine learning. So this has been super fun because I got to talk to some of you and like know what the different research, well, some of the different research groups in CDC are doing. And this is part of a BTech project together with Kilimanjaro. I see that some of you are in the team, so thank you for being here. So they are a quantum computing company based in Barcelona. They build quantum computers and also develop software solutions. And they're helping us understand potentially what can be done with quantum computing within computer vision field. So this, yeah, as I said, this has been very fun, also very challenging, because I think quantum computing and artificial intelligence are at different stages right now. But while as I will talk, as I will comment in this talk, I think it's very relevant to see what potential applications there could be in order to design quantum algorithms tailored to those, and also even tailor the hardware as it's being built to maybe be more specialized for potential applications. So this is a little bit about myself. And today I wanted to talk about quantum computing, quantum machine learning, and then some of the research lines that I've been exploring. So before going deeper into some of the algorithms, I wanted to give like some disclaimers. Let's say I wanted to talk about what quantum is and specifically what it is not. Right. So I always like to think about quantum computing using this metaphor. So the idea is that quantum computers and classical computers are the two different ways to process information. They're fundamentally different. So when I think about quantum computers, and when I talk to people who have never heard about quantum computers before, I use this metaphor. So imagine that you're exploring a new island. You arrive to a new island and you want to explore whereabouts. One thing that you can do is just walk around the island. This would be analogous to solving a problem by hand. You can do it, but it's pretty slow. It's a pretty slow process. And another alternative would be to use a classical computer. A car. If you take a car and explore the island, this would be analogous to using a classical computer, right? So that's going to be much faster. And finally, the last thing that you can do is rent a boat and explore the vast ocean surrounding the island, right? This would be the equivalent to using a quantum computer. So as you can see, classical and quantum computers are complementary. They are used to solve different tasks. And what I want to make clear with this metaphor is that quantum computing is not just the next iteration of supercomputing that would accelerate any computational task. So you cannot just take your transformer and put it in a quantum computer and it will automatically be faster. But it's a different way of thinking about information, of tackling problems, And potentially it can give you a very large speedup for particular tasks in the future when we have scalable quantum computers. And then, so the basic units of information in classical computers are bits, so you have a bit can have values 0 and 1, and then in quantum computers you have qubits, right? So mathematically you represent a qubit as a vector in a Hilbert space, and the unit vector, and then you have these properties of superposition and entanglement. For example, superposition is, let's say, the ability of qubits to be in a probabilistic combination of 0 and 1. So because you can express any qubit as a vector in a Hilbert space, you can express it as something like that. And then the physical property is that when you measure a qubit, it collapses in one of the basis states. And the probability of obtaining each basis state is the square of the amplitude, right? So in this case, when you measure this qubit, you get 80% of times the value 0 and 20% of times the value 1. So this is one of the properties that makes quantum computers so different from classical information theory. And the other property that is very much talked about is entanglement, which means that when you're thinking about systems of multiple qubits, you cannot think of them independently, but you have to think of them as a part of a larger system, so that modifying the state of one part of the system can automatically modify the state of some other part of the system, right? So you have to consider the state as a whole, not as individual tasks, like as individual states. And this is very different than in classical computers, because in classical computers, if you change one bit, this cannot affect the state of another bit. But in quantum computers, this can actually happen. And then there's another metaphor about how classical and quantum computers solve problems. And this is an analogy, so you don't have to take that literally. But I think it kind of gives you an intuition of which kind of problems could be helpful for if you want to solve them with quantum computers. So here you can see, for example, that the analogy tells you that with classical computers, if you wanted to solve a maze and you would want to do that with a classical computer, you would have to explore a single path until you hit it at that end, and then change the direction, explore another path, and so on until you find a solution. But with quantum computing, you could potentially explore multiple paths at once, and therefore that would be faster. Again, this is not literal. It's not exactly how it works, but it does give you an intuition of which kind of problems can potentially be suitable for quantum computers. So, for example, sequential operations, if you have the addition of multiple numbers, this is an operation that goes linearly with the number of digits of the numbers involved, and therefore it's suitable for classical computers and not suitable for quantum. This is also important. Not all the tasks that are suitable for classical computers can be efficiently simulated in a quantum computer. In this case, addition would not be faster with a quantum computer. On the other hand, the most famous quantum algorithm that is supposed to give us a quantum advantage is Shor's algorithm that's used for prime number factorization. And in this case, prime number factorization is very hard for classical computers because you have to, it's combinatorial, to try all the possible options, right? And with quantum computers, you can potentially try more options at once. And therefore, this is a great example for quantum computers and not for classical computers. The challenge here is that it's not so direct for other applications. So for every particular problem that you want to solve, you need to find the exact algorithm that solves it. And this is a very hard problem to do. So this is why quantum information and quantum machine learning is a very active field of research. Then another disclaimer about quantum computers. So you might have heard that quantum computers are not ready, like they don't exist in a robust, scalable way, and this is completely true. And for example, the algorithm, the Shor's algorithm that I told you that could be useful for prime number factorization, this one needs far more qubits, and qubits with far more like robustness to noise than the ones that we have today. So to apply this kind of algorithms, we would need fault-tolerant quantum computers, which means quantum computers are large and robust to noise, which do not exist today. But that does not mean that we can't do anything today with the quantum computers that we have. But in order to do that, we usually use either hybrid algorithms, which basically break down the problem into a quantum part and a classical part, and you run part of the algorithm in a quantum computer, part of the algorithm in a classical computer, and that gives you this wiggling room to put part of the problem in a classical computer, and therefore maybe you can have access to like wider like problems. But at the same time, you're getting some sort of speed up from the quantum computer. And then there's another type of algorithm that's called quantum-inspired algorithms. So these algorithms are meant to run in classical hardware, like in GPUs, for example. But they are inspired by the way quantum mechanics and quantum information works. So the most notable examples of a quantum-inspired algorithm are like tensor networks. So they were inspired by quantum many-body physics. And they use the notions of quantum information and quantum mechanics to describe the algorithms, but they have been used now in many machine learning settings, for example, for neural network compression by compressing the weights of different neural networks and therefore allowing you to save memory and potentially time. So that's the kind of algorithm that we can also use today because we don't need quantum computers to run them, just the quantum formalism as a design choice for this kind of algorithms. So anything that we're doing today in practice, it's not just theoretical, sits in between, well, between quantum-inspired and hybrid algorithms. And then, what is quantum machine learning? Why do we care about combining quantum computing and machine learning algorithms? Well, quantum computing is entirely about linear algebra. So when I talked about qubits, I talked about vectors in a Hilbert space. If I talk about quantum circuits, I would talk about unitaries. So everything, all the theory that is used to describe quantum theory is actually linear algebra. And it turns out that many machine learning algorithms are based on linear algebra, specifically the ones that were created when machine learning started, right? Like the more traditional machine learning algorithms, like cluster finding or supervised machine principal component analysis, they are based on diagonalizing a matrix, finding the singular value decomposition. And these kind of operations have a quantum algorithm that can solve this operation with a theoretical advantage, up to an exponential advantage. So one way of thinking of quantum machine learning would be, okay, let's take one of the linear algebra subroutines that we use in machine learning, put it in a quantum computer, solve it with a quantum computer, get up to an exponential advantage with that, and therefore solving machine learning problems in a much faster way. So that would be one way of describing quantum machine learning. So if that were, I could stop my talk here and go home. The only problem with that is to implement these quantum algorithms, you need fault-tolerant quantum computers. So you need what's called a QRAM, or RAM memory for quantum states, and you need millions and millions of qubits to implement this kind of algorithms. So this is not what quantum machine learning usually is today, at least from the practical sense. There are, of course, people doing research in this direction and finding novel algorithms, which is totally necessary for the field to evolve. But usually when we talk about practical quantum applications in the short or near term, we're not talking about this kind of algorithms. And also, as you can see, I've given you examples that are probably not what you're working with today. So you're probably not doing super vector machines, you're using transformers or more complex architectures, right? So even if we could solve that, this is probably not the state of the art of machine learning. So more realistically, what can we do with quantum machine learning today? So the disadvantage of what we can do today is that we don't have a theoretical guarantee. So now I cannot tell you, okay, with the quantum computers that we have today, you can get an exponential advantage. That is just not true. Everything that we have is heuristic. But on the other hand, everything that we have in classical machine learning is also heuristic. There's not a theorem that proves that a transformer is going to work, but it does in the majority of cases, right? So this is what we can hope to achieve with quantum machine learning today. So some of examples that we can, like some types of potential advantages that we can achieve with quantum machine learning today are, for example, encoding exponentially large data samples with fewer qubits. There are ways of encoding classical information in a quantum state that takes up to exponentially fewer qubits. So we could potentially take larger data samples and process them with fewer computational resources. Of course, the fact that you can encode them in a quantum circuit doesn't mean that you can extract useful information from it. So that's the heuristic part. It's not a promise, but it does give you room for these kind of calculations that cannot be easily possible with classical computing. Then another thing that has been seen empirically is that quantum machine learning algorithms tend to require far fewer training parameters to have the same level of expressivity. So a quantum neural network usually has fewer parameters than a classical neural network. So that also can give you reduced complexity and computing costs in that sense. Then another one is efficiency. So that's what we want, right? Like we want to run our models faster. Where can we get an improvement in terms of efficiency in quantum machine learning? Well, one of the options is to encode your machine learning problem as an optimization problem, as a combinatorial optimization problem, similar to the maze that I showed before, where you can explore multiple avenues at once. If you can do that with a machine learning problem, then you can formulate that as a optimization problem, and you can probably solve that in a quantum computer faster, or potentially faster than with a classical computer. And finally, well, quantum mechanics is weird, right? Like the theories and the properties that we see in quantum mechanics are weird. So that makes us think that maybe we can find novel representations of data using this quantum encoding. And this has been seen, for example, in kernels or in generative models, where quantum computing allows you to generate representations of data that are hard to simulate classically. Is that useful? Well, we don't know. Maybe in some scenarios it is useful, right? Because if we cannot achieve these representations classically, maybe they are useful to extract powerful data and perform more machine learning tasks. So these are the kind of things that we want to achieve with quantum machine learning today. And then, well, I wanted to talk a little bit about the areas of research that I've been working on. So I worked for a company for a few years, so I've been touching a lot of things here and there. But then apart from that, I did my PhD in quantum reservoir computing, and this is the main topic of research that I want to talk about today. But basically, reservoir computing, quantum reservoir computing is an algorithm originally designed for time series forecasting. That means propagating dynamical systems, or solving partial differential equations, or just doing like time series forecasting. And so I've been doing research in how to do that with a quantum computer, what are the advantages you can get, and then doing some like complexity analysis and like design choices in that direction. Then another area of research is quantum optimization for machine learning. This was one of the advantages that I was talking to you before. So for example, if you can formulate a problem in machine learning as an optimization problem, a particular optimization problem, then you might be able to solve that in a quantum computer. And examples of that are, for example, unsupervised image segmentation. So here we had a setting where we wanted to do image segmentation. Normally you would use, I don't know, a unit to do that. But in this sense, we had an unsupervised data set, so we did not have exact labels. And also we had like very few data samples, right? So in that setting, we formulated based on optimization problem that basically wanted to assign every pixel to like foreground or background, and then run this optimization problem in a quantum computer. This formulation is general, so you can run that in a classical computer as well, but running it in a quantum computer gave us some computational advantage in that sense. And then another example is feature selection. So imagine that in this case it was like a cancer data set. You had a lot of information from patients, but you had few patients, and you wanted to create a predictive model that helped you understand whether, well, like a diagnostic model, help you understand whether this person had a disease or not. But you wanted to select specific features that were relevant for the prediction. So again, we formulated this as an optimization problem where we wanted to either select or not select a specific variable for the prediction. And since this could be formulated as an optimization problem, we could solve it in a quantum computer. And finally, the third area of research was Bayesian networks. So Bayesian networks are these kind of networks where the child nodes depend on their parents based on some conditional probabilities. And this is probabilistic. And there are two areas that you could solve here with quantum computer. One is finding the structure of the Bayesian network. This is an incomplete problem, so a very hard problem. And again, it can be written as an optimization problem, which you can run with a quantum computer. And then even inference. So once you have the Bayesian network making predictions based on this Bayesian network, this is a hard problem in general. If the Bayesian network doesn't have like a very specific structure, then it's a hard problem. And with quantum computers, you can get up to a quadratic speedup with a full-term quantum algorithm, but that has been adapted to require less computational resources, so that more or less you can run it today. And I've been doing research about these Bayesian models in different application settings. So I know this is a lot. So today I wanted to just talk about quantum reservoir computing. First of all, because I know that in CBC, I haven't talked to anyone who has actually worked with the classical version of the algorithm, so I thought it would be nice to introduce it to you, and then talk also about the quantum version of it. So let me introduce you to reservoir computing. So we all know neural networks, right? The standard neural networks, they were like the feed-forward neural networks. They were designed for independent data samples. So if you have a sequence of data points, if you have temporal data, or you have text, these are not suitable architectures because they assume that that each sample is independent. So because of that, we designed recurrent architectures like LSTMs, then transformers, and so on. And these architectures are then suitable for sequential data. And these have been shown to be very effective in many settings. But what happens when you don't have a lot of data? So if you have a lot of text, yeah, you can train a transformer or an LLM or whatever. But if you don't, if you have a short time series, how can you train a recurrent model? So this is the question. And then one of the options is to use this algorithm called reservoir computing. This was actually proposed in the early 2000s, like in 2000, 2001. But it wasn't until like 2018 or so that it was proven to be useful, and then people started using it. And the idea with this algorithm is that instead of training a neural network, we're going to fix a neural network. So we're going to choose an architecture of a neural network, and then we're going to fix the parameters. And this is going to be it. And then with these fixed parameters, we're going to add another layer, which is going to be a linear layer, and that's the only layer that we're going to train. And by doing so, we're reducing the training parameters of the models to just like performing a linear regression. So that's very simple in terms of linear parameters. So we've reduced the complexity, we have fewer parameters, and then with that comes reducing the chances of overfitting the training data and requiring smaller training sets. And then the neural network can have a very flexible design. It doesn't need to be structured by layers, or you can choose basically whatever topology. And this gives us even the flexibility to choose other computational paradigms like quantum computing. And these algorithms became popular because in 2018, it was shown that it could be used to predict chaotic systems, like the time evolution of chaotic systems, which are very hard to predict by definition. And therefore, it was proven that this is an algorithm that's very accurate at predicting temporal dynamics. So just briefly, I wanted to give you the idea of why this even works, because it seems like a super simple algorithm, and it is. But the idea is that we have an input time series, and we want to predict the output. So if we have the input at time t, we want to predict the output at time t plus 1, for example. And then we're going to design a reservoir, which in the classical sense is a neural network with random connections and random weights. And the idea is that each of these weights is going to be calculated as a function of the input and the state of other neurons. What we want to do with that is generate similar dynamics to the input data, so that when we perform a linear combination of these dynamics, we can learn the true dynamics of our system. And why should this work? Well, what we're doing here is we're generating a set of dynamics that effectively form a subspace of dynamics that hopefully contains the true dynamics of our system. So for example, in this case, if we have like a periodic time series, the dynamics that we're going to generate are more or less periodic. If we have a constant time series, the dynamics are going to be more or less constant, or more or less differential, or more or less uniform. So in this sense, we do not want to be able to generate any time series, but we want to generate a subspace that contains our time series. And by doing so, and by using randomness, that's why we want a random neural network with complex architectures, we can generate a diverse set of dynamics that hopefully allows us to predict our dynamic. And so once we have created all of these set of dynamics, the only thing that we're actually going to train it's a linear combination of these that gives us the true dynamics of our system. And so we want this neural network to be very sparse and homogeneous. We want these different dynamics to be very different so that they span a larger subset. And this can be very flexible. This can be a neural network, or it can be anything else that produces a dynamical system. And well, these are the equations, as I told you, the internal network, like the internal nodes, are just functions of the input and the other neurons of the system. And the only thing that we train is this W out, which is the linear layer. And once it's trained, this can evolve autonomously. Okay, so as I said, this is very flexible. You can do this with a neural network, but you can also do this with any other type of system that allows you to produce dynamics. And in particular, you can run this algorithm with a quantum computer. There are different ways of doing that. The most direct, the most equivalent would be, let's replace the neural network by a quantum circuit. The idea is that each qubit would be equivalent to each node of the network, and the weight would be equivalent to the gates that you put in the quantum circuit to change the quantum states. And so in practice, how do we do that? Well, we're going to have some qubits that are going to be the input qubits. These qubits are going to encode our time series at different time steps, and we're going to be changing the states, artificially forcibly changing the states as we advance the algorithm. Then we're going to have the hidden qubits. The hidden qubits are going to have the memory of the system. They're going to remember past states. And then we have the measurement qubits. These are the ones that we're going to measure and be going to use them to make the predictions. This is different than the classical sense, because in the classical sense, you can observe everything and it doesn't matter. In quantum computing, if you observe something, you destroy it. So that's why we need qubits to destroy and use for prediction, and qubits that we need to keep just for memory. Why are you not working? Okay, and then the mathematical formalism needs to be done using density matrices. For those who know quantum, the idea is that we're going to be measuring some qubits, and because our qubits can be entangled between each other, we're going to be losing some information in the process. And so we need to be formalizing these using the density matrices. But the idea is the same. We encode a few qubits, we use a few qubits of the data. Then we apply a random quantum circuit. This is picked from, for example, a set of gates. I'm going to use this gate, and this gate, and then I randomly put them in the circuit. This is one idea. And then I'm going to be measuring the measurement qubits and use the results to make a prediction. And then, okay, so here I put some density operators. As I said, because I'm measuring some qubits. So the quantum circuit is represented by a unitary evolution. The results are represented by doing the trace of these observables. And then the state is represented by encoding the input qubit, tensor the partial trace of the other qubits. But in practice, if you want to code this with Python, what you do is you do something like this. So this is a quantum circuit, which wire represents a qubit. You're going to be encoding your data in one or some of the qubits with whatever encoding you want. You can use, for example, if your data is an image that's going to evolve, like a video, you can use an encoding that's particular for images. Or if it's something else, you can use different encoding. Then this is going to be your quantum circuit, your random quantum circuit. Here the randomness comes in the parameters of these rotations, but you can use whatever design you want. Then you're going to be measuring the measurement qubits. And, well, these measurements are going to be used for predictions. And finally, the input qubits are going to be reset and then reinitialized again to continue this process for all the training steps. So this is a little bit how you implement quantum measurable computing in a digital quantum computer. And then what I've been doing in this setting is analyzing how to generate this random quantum circuit. So here I put an example of a random quantum circuit, but it has a very clear structure, right? Like you can see that this is not random in the sense of a random design. So here what we saw is that actually the way that you design these quantum circuits has a huge impact in the performance of your algorithm. So I won't get into many details today because it was more introductory, but what we studied here was what is the complexity of the quantum circuit that you need to achieve a certain level of performance. Quantifying the complexity, that's an open question. But just to give you a sense, you can fix a set of gates. For example, I say I'm only going to use an X gate, a CMOS gate, and a Halberg gate, for example, or this set of gates, or this set of gates. And then I'm going to put these gates randomly in a quantum circuit. So if you use this set of gates, this represents a subgroup of the Clifford group. This is classically simulatable. So this is something that you can classically approximate, no matter how large the circuit is. And this as well. This is a bit more complex, but it's still classically simulatable. This one, on the other hand, is universal. Universal means that you can perform any quantum operation only with this set of gates if you put in all of them. So what we saw, and finally, these ones are diagonal gates. These are a type of IQT circuits, and these are not universal. You cannot perform any computation or any possible computation, but they are hard to simulate classically in some senses. And what we saw during experiments was that actually, if your circuit is universal, you get a better performance. And this is because this circuit is more expressive. It can extract more information from your data. And hopefully some of this information is going to be useful. So when we talk about like diverse trajectories in the classical sense, here we are achieving this diverseness using universal sets of quantum gates. And what we're working on now is characterizing this even further. If we look at specific topologies of quantum circuits, how much expressiveness do we need versus computational cost, and how can we measure this in a scalable way? Because these kind of measures work if you have 8, 10 qubits, but if you have 100 qubits, they become hard to calculate. So the line of research that I'm exploring now is how to measure this complexity in a scalable way, and how that's related to performance in different settings. Okay, and finally, I wanted to talk about different examples of quantum reservoir computing, different applications. The first one that I did my thesis was for financial forecasting. So here we wanted to predict the prices of different agricultural products. So we called this a zucchini paper because we were predicting the prices of zucchini at different time sets. And the idea is that we had a rather small data sets because the prices were aggregated weekly. So even if you had a few years of prices, you had 400 samples, something like that. And then these prices were very volatile. They changed very fast, and they were highly influenced by external factors. So it was a time series that was hard to predict. So here we trained different models. We trained quantum reservoir computing, and LSTM and SERIMA. We tried to train a transformer as well, but it didn't really work with the size and complexity of the data that we had. And so what we saw with quantum reservoir computing is that this model was actually able to capture abrupt market falls. So when the price was dropping very fast, this was the only model that was going to predict that the price was going to drop. And when there was like a lot of volatility, the prices were going up and down very fast, this was also the only model that could actually really predict this kind of changes. And then you might ask, okay, why don't you just use classical reservoir computer for this? Yeah, sure, you absolutely can. It worked well as well. We had very similar results with classical reservoir computing. The only difference is that with classical reservoir computing, we needed a neural network with around 150 nodes. And with quantum reservoir computing, we only needed 7 qubits to achieve the same level of performance. Of course, it doesn't matter for the scale, but then we started looking at different time series that were correlated. And in that setting, having fewer computational resources, like fewer qubits, gave us more expressivity. Because again, we have very short data sets, like we have very few data samples. So you increase the number of features, you're increasing the number of training parameters as well. And therefore you start with your training data. With quantum reservoir computing, we were able to reduce that and therefore train a more accurate model in that sense. But like from a calculation point of view, both models should be able to extract information from data. So this is like the most like canonical example. And then we've also used reservoirs, not quantum reservoir computing, but reservoirs for other settings. So for example, we use this for our regression problem in quantum chemistry, which is we wanted to predict the excited energy states of some molecules. There's a very well-known algorithm to calculate the ground state. But then if you want to calculate higher energy states, well, you can do it, but you have to keep adding terms in the loss function. And then if you want to calculate the excited state number 35, there are a lot of terms in the loss function, so it's hard to optimize. So what we did here is, okay, let's use this quantum algorithm to get the ground state, and then send this algorithm to a quantum reservoir and try to predict the excited energy states. And we were able to do that for specific designs of quantum reservoirs that were like complex in the sense that I mentioned before. So that's another type of application. And finally, the last thing that we did was use quantum reservoirs to compress neural networks. That means to replace a convolutional layer of a neural network with a reservoir that has no training parameters. So that if that works, you saved all the training parameters of the convolutional layer. And this was used in a setting of drug discovery, where we're trying to predict what's called the binding affinity, which is the strength of interaction of a protein and a potential molecule, like a potential drug that you're going to take. We wanted to know how much they would interact when you took them. And what we did here was, as I said, like we had a convolutional neural network. Our input data was pretty large, like 48 times 48 times 48. This represented the drug and the protein in space. So this was a very high dimensional data. And therefore, we had a convolutional neural network with 10 million of training parameters and not a so large data set, so that took time and kind of overfit the training data. So what we did is we replaced one of the convolutional layers by a quantum reservoir, so that the quantum reservoir did not have any training parameters, and we tried different reservoir designs. And by doing so, what we did is we reduced the 10 million training parameters to 8 million training parameters, and that resulted in a 20 to 40% in saving times and GPU costs, depending on the network. So basically, by doing so, we were able to effectively compress one of the layers of the convolutional neural network. And what we saw is that for specific quantum reservoir designs, we achieved the same performance as the original convolutional neural network, while with other reservoir designs, we achieved the equivalent of just having like a random convolutional layer here with random parameters. So in this context, the quantum reservoir was accurately replacing the role of the first layer of the convolutional neural network. So these are just like general applications of what we've done. And finally, something else I'm working on is trying to entangle two different types of data. So if you have a time series and an image, can we all encode both of them in a quantum circuit and kind of entangle the information so that we don't need different models to treat different types of data? That's an ongoing investigation. And finally, the last thing I wanted to finish, this talk about is talking about a little bit of what I discovered from these weeks at CDC. So these are very high-level, raw ideas, but after talking to some of you, these are some of the first things that come to mind when I think of applying quantum machine learning in the context of CDC research lines. For example, in autonomous driving, here quantum reservoir could potentially help model temporal driving scenarios. So usually we take each time step, each picture as independent, like this is all the information that we have. But if we could somehow retain some information about previous frames, this could potentially give more information. But again, this is computationally very prohibitive. This is definitely out of the size of what quantum computers can do today. But in the future, this could potentially help, especially if we can use quantum reservoirs that require exponentially fewer qubits. So this could be an idea. Another line of research that we have at this group is generative models. It's not what my main work has been until now, but we have a strong quantum research line in that direction. And so another thing we could do is use quantum generative model to generate equivalent trajectories, because when you're driving, you usually there are a lot of equivalent trajectories that don't change the outcome, but they are all valid. But you're not going to just drive and do the same route and then just turn a little bit to the left and turn a little bit to the right, because that wastes a lot of time. So if you can generate like equivalent trajectories to train then other models, maybe we can do that with quantum computing by generating, well, by using quantum generative models that are hard to simulate classically. So maybe we can learn something new with quantum generative models. And we're probably not going to do that at the pixel level, because that's totally out of the scope of what quantum computers can do today, but maybe in some latent space, or maybe just given instructions, as in turn a bit to the right or turn a bit to the left. Maybe that's something that we can do with quantum computers. That's for autonomous driving. Then I just want to give you like one or two examples for each. But for document analysis, well, I have you guys looking at me, so sorry if I say something wrong. But one of the areas that we have explored is regarding to style transfer. So if you have like, if you want to train a handwritten text recognition model, but you don't have enough data from one specific author, maybe what you can do is take another author that does have like a larger data set, and then do style transfer to like write the same documents of like the larger data set with the style of the first one, and then train a model with that. So that's probably something that that you can do. And one thing that we're exploring is within these generative models, maybe we can incorporate some quantum layer that helps increase the diversity of the data set that we achieve. In coloring context, we've seen that they're using neural wide field, and actually we had a master thesis working in a quantum version of this, so this would be a potential area of interest. Then learning on machine perception, they're working a lot with diffusion models and generative modeling, and it was one of the most intriguing conversations that we had. We learned so much. One of the things that they're working on is privacy preservation for diffusion models. So trying to like not allow the users to retrieve information from the training set that was used to train this model, because this means that they can steal information, for example, from artists, right? So if we train a model using some artistic information and then you can go and retrieve it, you get information from the original training set, and that information can be sensitive and private, right? So here, one of the areas that we're exploring is using tensor networks, which is one quantum-inspired algorithm, to replace some of the layers of the diffusion model. Instead of using neural network layers, we would use a tensorized version of them. And there are some papers that have shown that by using this tensorized version, that having access to the training parameters of the models is equally, like, gives you the same information of just having access to the model. So in the cases where you share the parameters of your model publicly, if you tensorize your model in this way, these parameters do not give you more information than just having access to the model itself. So that could be a way to improve privacy in these settings. And finally, in multispectral image analysis, we're looking at some resolution invariant super resolution. So there are these Fourier neural operators that help you, well, they're like a class of neural networks that are invariant to resolution. So they are invariant to the size of the image. And this would be very relevant in this setting. And there are tensor network versions of these kind of algorithms that can help you compress and save memory in these settings. So this is another area that we're exploring. That is to say that there's a lot of things that could be done within the quantum machine learning and quantum inspired world. We just have to find the right ways of thinking about the problem. So thank you so much. And if you have any questions, feel free to ask. Any questions in the audience?
Thank you for the talk, very interesting. New class. I have some questions. The first one is curiosity. You mentioned at the beginning entanglement, which is a very great thing for if you think about. So is this entanglement something that you can force, or something that you are actually using in current quantum computing somehow?
This is, I mean, you can build states that are entangled, and entanglement is usually part of the algorithms that we're using. So when I say this is easy to simulate classically, if it's easy to simulate classically, it's usually because there's not a lot of entanglement. If there is a lot of entanglement, it's usually not efficiently simulatable classically. So this is, you can build this state if you want, and this is usually present in the algorithm that you design.
So you mean that this entanglement can be simulated in quantum computer simulators?
You can simulate it, and with 2 qubits, you can simulate anything, but it's not scalable. Like if you want to simulate a lot of entanglement with 100 qubits, it will take forever to simulate, but you can run it in a quantum computer.
And another thing is that in this reservoir concept I have shown in the picture, this one, this reservoir computing, I'm not sure if these small balls here are neurons or are neurons. What are these?
No, these are neurons. These are like functions. So each x, this x is a vector that represents the values of these neurons for each time step. So for each time step, you're going to change the value of x for all of these. And what's random is the connections. So the matrices W here. This is what's random and randomly selected before you check the output.
So what means that you are that 2 neurons are connected to each other in the both directions?
It means that this matrix has a number different from 0 in the row and column that connects these 2.
Okay, but I mean, to me, these connections that are here, I understand these connections as the output of one of the neurons go to the input of the other.
Mm-hmm.
And since you have double-directed connections, it's like they happen in different times, something like that.
No, it's not about time. It's about these, for example, these 2 are connected. This means that the value of this node depends on the value of this node, and the value of this node depends on this node. In this case, the value of this node depends on this one, but this one does not depend on the value of this node. It means that it's not symmetric, the matrix.
Is it like a graph neural network? Is it that you're summing a function of a node to the function of the other?
No, graph neural networks are far more complicated. Like this is all the equation of the.
Oh yeah, I mean, such passing algorithm. Are you literally summing one ball to the other ball?
Yes, times scaling.
Yeah, then it's a graph neural network. And it's a message passing algorithm, but you're not learning the weights.
Yeah, you're not learning the weights. You can also depend on yourself and the input in this sense and the previous output. So it's like it has more flexibility in this sense. But yeah.
This is a bit curious because this reservoir thing looks like in traditional machine learning when you have a mixture of different experts that are coming from different kind of algorithms. Then you somehow mix these experts. I didn't expect that this was so good, let's say, because it's an old idea.
Yeah, no, it's definitely old idea. And pretty simple. Just that, yeah, like there are some theoretical proofs, I haven't put them here, but there are some theoretical proofs that if you can guarantee something about the eigenvalues of these matrices, then you have for sure that these functions do not depend on the initial states. That you forget all the initial states of everything, and therefore you're retaining. There's a bijective function, so you're retaining all of the information from the input. So this paper came as a completely theoretical paper, so it has very solid grounds, and then it was proven that it has applications.
My last question is curiosity. When you are working on these things, are you actually working with a quantum computer or with a simulator of a quantum computer?
Both. Like when you do tests, you run it in your computer and see what happens. But quantum computers can be accessible through the cloud. For example, IBM has an open quantum computer that gives you access for 10 minutes a month, something like that. And if you pay, you get access. So for larger simulations, you have to run them in a quantum computer, and you cannot simulate 100 qubits in any computer, like any computer. So it's a bit of both, but of simulation to test.
What is the cost of simulating 1 hour in this IBM, for instance?
I have no idea. I don't know if anyone from the. It's very expensive, much more expensive than GPUs. Yeah, but usually there are like agreements between like a university and an IBM and things like that. And from Teams, any questions? Feel free to just unmute yourself and talk.
Laia, thank you for the presentation. There is a question asking, can you comment on the readout of quantum reservoir computing with respect to the classical reservoir computing? In quantum mechanics, we usually measure the expectation of some observables with more than once.
Yeah, here as well. I mean, it's a very flexible design. If you want to measure the state in the computer, like the whole counts, like the whole quantum state, you can do that, but that's not scalable. So usually what we do is we measure local operators. Yeah, and again, it has been shown that with local operators, it's usually enough to then train a classical machine learning model, like a linear regression model, to just calculate a linear combination of these expected values and predict the outputs. The difference with classical reservoir computing is that in classical reservoir computing, you take the exact values of the nodes, so these x functions, which are these trajectories of every single node, you take that to make the prediction. It's just a linear regression based on that. In quantum computers, quantum computing, you cannot just take the state of the qubits and make the prediction, because to take the state of the qubits, you have to measure the qubits, and to measure the qubits, you're changing the state of the qubits. So what you're doing is you're going to choose a fixed set of qubits and measure something, some property of them. It's usually, the expected value of some local operator, because that's what's easy to calculate with quantum computing and scale.
I'm curious, in my ignorance, because I really don't know much about quantum computers at all, but to the best of my knowledge, there are various types of, let's say, quantum technologies and quantum computing technologies. I know, for instance, that Microsoft invested very heavily in one kind of technology that is different for instance, from Google or IBM. Or if I here does something different, the Kilimanjaro does something different, and so on. So are all of the techniques that you show here applicable in any computer? Are there any properties that are favored by some architectures? What does the ecosystem look like?
So I would say that there are majorly two types of quantum computers in the sense of how they process information. These are digital quantum computers, meaning that you have qubits and you have gates. So this is analogous to the classical computing when you have logic gates that change the states of the bits. For this kind of digital quantum computers, this is a mathematical formulation, and then you can run them in different devices. It doesn't matter. The only difference is that each device will have their native gates, the ones that they are actually implementing, and then any other gate has to be transpiled and converted into these gates. So it's usually, it's better to choose a quantum circuit that already uses the native gates of the device that you're going to use, because otherwise you're going to need more transformations, and since there is noise, you're going to get worse performance. Then there's another type of quantum computers that are called analog quantum computers, and that's what Kilimanjaro is mainly building. These ones are dedicated at performing the time evolution under a certain Hamiltonian. So you have an energy that's governing the system, and then you evolve based on that energy. And what you can control is the energy, the interactions of the different particles. That's a very different type of quantum computer. It's not represented by these kind of circuits. This can definitely also be used for quantum reservoir computing. In fact, both lines are very active. I just chose to talk about this one because it's more similar to what you would do classically, so I think it's easier to understand. But in that sense, what you have to control is what is the energy of the system. And based on what energy you choose, you're going to have, again, better results or worse results.
in practice, these kinds of computers look a lot like, with a bit of jump, like an FPGA of sorts.
Yeah.
Thank you.
Any other comments? Okay, well, I think I've bored you enough, so thank you all for coming. Yeah, and feel free to ask me any questions if you see around. Thank you for coming.